So good morning, good afternoon, everyone. I am Emma Bordier, currently enrolled in a co-supervised PhD, my home university being in Leuven in Belgium, but currently I am at ISO in Chile, and that's why I would like to thank the organizers for moving my talk later today. So today we'll talk about how to prove the multiplicity of massive premium sequence stars with VLTI gravity. Okay, so first to give some general context. So massive stars are powerful machines. They are known to have contributed to the re-ionization of the early universe and also to have helped in the formation of the first galaxies. They drive the chemical and the dynamical evolution of the galaxies, and their study is of great interest because they end their life in powerful explosion, and as such, they hit and they enrich the surrounding gas clouds and trigger the new generation of star formation. It's like the great cycle of life. So if I can paint the portrait of massive stars, there are stars with initial mass greater than 8 solar mass. This mass was set because starting from 8 solar mass, the wind's ionization have effects, and also it's the limit for core collapse depending on the mass loss, and the feedback to the galaxy is also tremendous. So the formation timescale is about 10 to 5 years. The lifetime is a few million years. So these two scales are very short compared to the sun-like stars or to intermediate mass stars. And on top of that, a very important feature and characteristic about massive stars is their multiplicity. More than 90% of OB stars are in multiple systems. So multiplicity plays a pivotal role in the evolutionary path of massive stars and hence in the orbital parameters. So let me quickly give the state of the art of this multiplicity property across the evolution of massive stars. So first, if I can start with the main sequence, some studies have been done in the past to measure this multiplicity among a significant population of massive stars on the main sequence. And they found that binary interaction, dominates the evolution of O-type stars for about 90%. And even if we go even further, a third of high mass stars are part of a triple star system. And then they used direct measurements of the orbital period distribution, and they found that there is a high tendency towards short period binaries, meaning binary periods of less than a month. They tried to reproduce and recreate these measurements in in a population of premium sequence stars. And for that, they probed for multiplicity in the M17 star forming region. And they used radial velocity measurements for that. So in short, radial velocity measurements relate to the presence of close companions. A large radial velocity would refer to a close binary. And then there is the radial velocity dispersions that probes for the variety of multiple systems that you have for a given region. And what they found in M17 is that there is a low binary fraction. That means that there is a lack of short period binaries, and this result was further confirmed in other young clusters. So we can ask, like, what happens between these two regimes to make them close binaries and to meet what we observe for the main sequence stars. So as I said, multiplicity would play an important role in settling close binaries, and one of the scenarios that is trendy right now is the migration scenario. In which binaries are formed at large separations, and then they harden on a timescale of 2 million years or less to leave the system as a tight system. And to produce these close binaries, it can be done through two main channels. The first one would be the interaction of the companion with the remnant of the gas and make it migrating towards the primary star, and the second channel would be the interaction with outer star, a third star, in the surrounding accretion disk. And that's why, like, studying multiplicity is very important to know if these objects can have any impact on how the closed binaries are formed. So this is where my project comes in, and what I will talk about today is what are the multiplicity properties of massive stars at the latest stages of their formation. So first, we have to find the best object to observe, because my research is mainly focused on observations. So I also worked on the M17 star forming region because it's located in the Sagittarius spiral arm, and is one of the closest, most luminous, and youngest star forming region in our galaxy. So there is like a wide variety of stars in there, and there is especially this cluster, the NGC 6618 cluster, at the very center of M17 that hosts a lot of young massive stars. So my sample is composed of 6 young O-type stars. They are the brightest ones in the region, and also of luminosity class 5, meaning that they have probably reached the 0-age main sequence already, because we cannot find any feature or trace or signature of accretion disks, and 5 spectroscopic companions were reported around these stars. And then, like, once we have the object, we have to define the wavelengths, the technique, and the instruments we want to use for that. So young massive stars are deeply embedded. They peak around 100 microns, so we have to observe them in infrared to maximize the flux we receive from them. And also, we would like to resolve the binaries to test for this migration scenario. So we have to look for high angular resolution facilities. So the best compromise would be to observe them using near infrared interferometry, so gravity with the UTs, given the faintness of the objects. Cool. So as it has been explained this morning, 2 very important observables in the interferometry, if not the most important observables, are the visibilities and closure phases. So I use them to probe for the multiplicity. So the closure phase, they trace the asymmetries in the system, such as different brightness in the binary system, or the presence of an asymmetric disk, for example. And the visibilities, they stand for the contrast of the fringes. So for especially resolved objects, a decrease in the fringe contrast would be like a drop in the visibility amplitude. So by measuring this drop in the fringe amplitude, astronomers can measure size, shape, and features of the star, or probably multiplicity, as it is the case for me. And for that, I use Pemoirhead also, the tool that has been developed by Antoine Méran. And I can build some model using different geometries and building blocks. And the fitted parameters are mainly the position of the companion and the flux ratio. So the results are on the right panel. Over the sample of 6, I found 3 binaries and 3 triples. So the physics that is coming out of this result is these 2 main results, that are the multiplicity fraction and the companion fraction. So I compared my result with different populations of stars from 0.1 solar mass to 40 solar mass, regardless of the environment and the evolutionary stage of the sample. What matters here is the mass of the primary star. So in both panels, you can spot my data point is the red data point, and this has been compared to the study of the gravity collaboration in Orion, and also to the SMASH data of UXANA limited to the O dwarf. So the most striking result will be the compatibility of our result with the ones of gravity collaboration in Orion. Orion is a bit older than M17, but still a star forming region. And they also agree with the results of SANA. What differs slightly would be the size of the error bars, but this is mainly due to the sample sizes. Something else that is very interesting would be like the separation to the primary stars. So you can see the resulting brightness contrast as a function of the companion separation in milliarc second. And also I added other interferometric campaigns, both with gravity and Orion. So there is no significant relation between the magnitude difference and separation but there is a clear lack of detection below delta mag of 2 here and companions within 3 milliarcsecond. And this is mainly due to the current sensitivity of Pioneer and Gravity. So we can see that with combining interferometry with other techniques, we can probe for either closer or wider companions, and this will give like a bigger picture of the environment of massive stars from 0.1 milliarcsecond to several hundreds or even thousands of milliarcsecond. And
you have 2 minutes.
Okay. Yeah. Cool. And this is this plot would be very important to for the consequences of star formation and especially about the migration scenario. So if I can give you some conclusions, 100% of the multiple systems at the zeroed main sequence that populate my sample have 2.3 companions on average at the traced scales up to 120 AU in the M17 star forming region. And also, despite the cluster environment and age, M17 shows consistency with the previous studies in terms of multiplicity and companion fraction for the O stars populations. And some future work. It would be nice to answer the same question, but in earlier stages, so to catch the processes that shapes the binaries. Because now we have like the state of the art on the main sequence of multiplicity on the main sequence, pre-main sequence. So it would be nice like to study a bit these formation stages of the widely called massive young stellar objects. And for that, I got time allocated in priority A for the ongoing period P109 to observe 14 MY-SOS in M17 with gravity and still the UTs. So we will be able to probe for the earliest stages of massive star in this same M17 region. And now I am currently working on another project with NACO imaging data, and I also study the multiplicity of 13 MY-SOS in our galaxy. And so it will be very interesting to compare those results and state the first conclusion about the multiplicity systems, and also to see what we can learn from the cluster environment and the properties in earlier stages, and how these new insights fit in the general picture of star formation. Thank you for listening, and I'm happy to take questions.
Thank you very much. Any question from the hall? Please tell your name. Not yet. Then from online. Okay, I don't know who was first, Konrad or Anton. Konrad, please.
No, sorry, I didn't have.
That was on. Okay, okay. Then let me ask in the meantime. My feeling was that this kind of multiplicity studies maybe could be done in the radio regime also, so with the long wavelengths VLI, or isn't it a good way because there you also have the spatial resolution?
Yes, sure. I think we can go, for example, for ALMA and also probe for this for this multiplicity. But I think that with ALMA it's maybe too, I don't know, too wide, and but it would be also very interesting, like for example, to trace like the dynamics of the disk in these very young objects, and it could also help, for example, for the migration scenario to know whether there is still like this interaction with an accretion disk or so. But yeah, that can be done with radio for sure.
Thank you. Any question? If no more question, that thank you again.
Thank you.